Okay, so for part 2 of homework 9-2 here, we really just have question 13 to wrap up. And I'll go ahead and do kind of a slow transition down so you can see this if you want, and then see the final answer. All right, so there's our final answer down there. If you've got that and you're confident, obviously feel free to stop the video here. You're done. Congrats on finishing homework 2. If you do need to see or hear any explanation, I'll go back through and I'll give a brief explanation of this as well. So coatings and films can be kind of tricky, right? This is definitely the definition of a coating because it goes from air, which has an index of 1, to the oil, which has an index of 1.375, to a glass surface, which has an index even higher than that of 1.537. But anyway, the key concept, the key that you definitely need to be comfortable with. So what happens to light as it reflects backwards? Because ultimately, we want to compare the first reflection here to the second reflection down here. Right? We want to compare those two so that we know if they're going to meet up in phase or out of phase, right? And so with each of these reflections, anytime you go from a low index to a higher index, or in other words, from a higher velocity to a lower velocity, anytime you go from low index, high index, or high velocity to low velocity, the reflection is going to be knocked out of phase with the original wave, right? So this wave right here is out of phase with regard to the original wave. The light, however, that passes through is still in phase, so this is in phase with the original wave, right? But then at the second boundary, again going from low index to high index, it once again bounces out of phase with the original. So with respect to each other, right, these two are both out of phase with respect to the original wave, which means with respect to each other, they're actually by nature in phase, right? These two waves right now are actually in sync. They're in the same phase as each other. So if we want them to constructively interfere, we would want to preserve that in phase by preserving that difference of a full wavelength. If we want them to destructively interfere, which is what we want here because we want to reduce the reflectivity, so if we want to minimize the glare, if we want to reduce the reflectivity, we want these two to be out of phase. So in order, because they're both out of phase with the original, which means again they're in phase with each other, in order to set them out of phase with each other, we've got to set them off by half of a wavelength. Right? The second one down here is going to have to travel half of a wavelength further than the top wave in order for it to be offset, right? And that's the minimum thickness there, right? If it's 1/2, could also be 3/2 or 5/2, but the minimum thickness is going to happen when it's 1/2, right? So anyway, I have to do a little bit of work here. The trick you do have to watch out for is we don't just want the wavelength in air, we want the wavelength in the glass or in the film in this case, right? In the oil in this case. So I use the index to help me find the velocity in the oil. The index is the speed of light over that velocity, so the speed of light 3.08 or 3.0 times 10 to the 8th. The index here 1.375, so I can find my velocity in the oil itself. I don't care about the velocity in the glass because the wave is only traveling down and back in the oil, right? It's not in the glass as it goes down and back. So that part isn't relevant for my calculations. But anyway, I find the velocity in the oil there. And then they actually were nice on this one by giving me the frequency, and I know the frequency stays the same for both the air and the oil. Right, so I've got the velocity in the oil, I've got the frequency in the oil and in the air. So I can find my wavelength in the oil, and then from there again I know that the wavelength is going to help me find the thickness of the film, the thickness of the oil layer. Right, so the only significance here is it's 2t because it does have to go down and back. Right, and it's equal to 1/2 the wavelength. So 2t has to be offset by 1/2 the wavelength. So then t equals 1/4 the wavelength, and then just plugging in my wavelength, easy enough to see from here. So definitely a big question. You get a lot more practice with this in in homework 3. So if you're not comfortable with this one yet, we'll get a lot more practice with this as well in the third homework assignment. But definitely something you guys want to make sure you're comfortable with. Do let me know if you have any questions with this. I know it can be tricky at first, but once you get a hang of this, it's actually not a bad process. The biggest tricks to watch out for are making sure you find the wavelength in the oil and not the wavelength in air, right? And again, the reason for that is it travels down and back as it's in the oil. It doesn't travel down and back in the air, right? This wave that's making up the extra distance is traveling down and back in the film, in the oil itself, and not in the air. But anyway, that's enough rambling for now. If you do have any questions, come find me.